Alright, I want to go ahead and get started on analog circuits, and throughout this course we'll deal with analog circuits and we'll deal with digital circuits, and I'll talk a little bit about each. The analog circuits part, you'll have seen part of it before. We're going to talk about Ohm's law and series and parallel resistors and all that. The digital circuits you probably haven't seen, and it's not traditionally put in chemical engineering curriculum, so I think it's something that this course has to offer that you may just not see other places. So anyway, I'll go ahead and get started. And there, jumped ahead of all of them. Okay. Well, you've seen Ohm's law before. I think in physics class here you deal with Ohm's law, but you may not have actually thought about the implications of Ohm's law. And so there it is. E equals IR, or voltage equals the current times the resistance. And of course we can solve for any of these variables that we might need. But the important part of this is voltage is across a component. And so what I mean by that is that you never just talk about a random voltage. You never, like when somebody says 9 volts, they mean 9 volts with respect to ground. Voltage is always specified with respect to ground. It's either across a component, so basically between the two terminals of the component, or with respect to some ground. Current is the amount of electrons that flow through a component, and so it's not just the amount, it's the flow rate through a component. And then resistance is how much the device is impeding the flow of those electrons. And every device has resistors. I don't care if you've got a piece of copper wire, it's got some resistance. And if you think, if you think it doesn't, make a long enough copper wire and it will definitely have resistance. The resistance basically converts the electrical energy into heat, and so that ends up being a really big deal for either high current applications or even microelectronics, where you're taking components and shrinking them down, and maybe you have a bunch of like transistors on a computer chip, and with such tiny little spaces to work with, it's actually hard to get the heat out. So I'll talk about that later on in the semester. However, the classic analogy is to think of this like water flow, where voltage is like your water pressure, current is like your flow rate, and resistance is basically like a critical orifice or a nozzle, such that it's impeding the flow of the water. And so we'll talk about that off and on throughout the semester. You'll be obviously expected to know Ohm's law and how it works and be able to solve for any of the components. The other important thing with Ohm's law is in instrumentation, what we care about is measuring these quantities. And so when we go to measure voltage, we measure it in parallel or across the component. When we measure current, we have to put it in series with the component. And the resistor, we actually have to take the component out of the circuit so that there's not existing existing current flowing through it. But I'll give a separate lecture on how to do each of these measurements, complete with a multimeter, because you'll need that for one of the labs here. So you may wonder why we would care about resistors. We go to all this trouble to convert mechanical energy or thermal energy or sunlight or whatever into electrical energy, and then the very next thing we do is put a bunch of resistors in there to slow it down and convert it back to heat. There's a lot of reasons why we would do this. I put up here limiting current, biasing transistors. Sometimes we use resistive heating. That's always a good thing. Sometimes we change the resistance with a potentiometer, and that's really useful for things like tuning circuits. So in your car radio, if you have a knob or buttons to switch stations, what you're actually doing is you're changing a resistance, and that's tuning a circuit. Anyway, there's lots of reasons we care about resistors, and I put up here a couple other things. They're measured in ohms, and so an interesting thing with resistance is it's one of these physical properties that varies by many orders of magnitude, and you can't just look at a resistor and determine how much resistance is there. If we were in a physical class, I would show you some different resistors, but in your kit you've got I think 4 different resistor values, and you'll notice they're all the same size. They're all, just a little tiny resistor, yet their actual resistance varies quite a bit. I think there's a 390 ohm resistor and a 2.2 kilo ohm resistor, and they're all in there together. I could have given you the 1 mega ohm resistor, and it would have been the same size in this case. So it's one of those properties that you can't just scale up the size of something and expect that to change the resistance. But often bigger resistors can withstand more power. So when you're converting this energy into this electrical energy into heat, a bigger resistor can dissipate more of that heat before it melts or burns down. So that's why there's different physical sizes of resistors, and so I just want to make sure I pointed that out. So I'll go through a couple examples here, and I'll draw these out, but just as kind of a review from physics class, series and parallel combinations of resistors. If we have a couple resistors in series, meaning the same current passes through each of those resistors, we can just add the resistances together and then model it as one big resistor, or one resistor with higher resistance. And so that's what I'm trying to show there. For parallel combinations, parallel just means that they have the same voltage across each of the components. And so it's actually this inverse addition rule, where our equivalent resistance is like 1 over our equivalent resistance equals 1 over each of the resistors added together. And I'll go through that here in a minute. So I mentioned the sizes and how we can't just look at a resistor and tell. There's this resistor color code, and so you'll notice on your resistors there's these little color bands, and first band and second band are basically your first 2 digits, and sometimes there's a third band. Basically if you have a 5-band code, you'd have a third band that's just more precision. But then the fourth band is a multiplier. So you take whatever you get in these first couple bands and multiply it by this. And you'll notice they're all products of 10 here. So it's basically like whatever you get times 10 to the whatever color here. This is convention. This way you can put little tiny colors on resistors and know what value they are without having to write in a number and have somebody read on little tiny resistors. I will caution you though, it's just using the resistor color code. First off, there's a good percentage of people that are in fact color blind and may not be able to distinguish these colors. Also, these are just electrical components sitting in a box somewhere, and these colors can fade and darken, and all depending on what dyes are in there. I'll be honest, the red, orange, and brown look really similar unless they're all next to each other and you can distinguish them. If I just pulled one out of a bin, it would be really hard to see. And sometimes the blue and purple also will look very similar. I also mentioned there's a tolerance. The last band here is a tolerance band, and it's basically plus or minus some percentage. Most of the stuff we're going to use in this class is going to be, I think most everything I've given you has been the 5%, the gold band there. So if your resistor's 100 ohms, they're supposed to be 100 ohms. 103 ohms might be a valid resistance for it. And I think that's mostly what I wanted to say on this resistor color code. I also did want to mention, so resistors, thanks to Ohm's law, resistors are a linear component in that current flows, and we know V equals I, or E equals IR, so we can find a slope, and the intercept's going to be 0, and it's a nice linear device. Another important device that you're going to use in this class is a diode, and diodes are not a linear device. Their resistance, I'll draw a graph of it, but basically you need a certain amount of voltage before it does anything at all. And depending on what the diode's made out of, it'll be a different voltage. and sometimes it's called the knee voltage or the turn-on voltage or whatever. A couple important things. It's a semiconductor device, and I'll talk a little bit about semiconductors off and on throughout this semester. But they also only conduct in one direction. So if we use our water analogy, our water flow analogy, a diode is a lot like a check valve. So current can only pass in one direction. So looking at the schematic symbol down here, in this case, current would flow in the direction of the arrow. So it would go from the bottom to the top in this case. Your LEDs are just a light emitting diode. So some of that energy is converted to light, and so you can see it. And depending on what wavelength your LED, the voltage that is required for it to turn on is going to vary. So I think I gave most everybody in your kits yellow or red LEDs, and I think they're around 2 to 2.2 volts to turn on. Some of your blue and green ones are 3 volts. And I just want to throw out there something about LEDs too. I was an undergraduate. It seems like it was a long time ago, but early 2000s, I was taking all these semiconductor classes, and at the time they said, you will never see a blue LED. Such a thing cannot exist, will not exist. The quantum physics professors up there explaining why it's impossible, and this is just never going to happen. You'll never see one. And I don't know exactly when the first blue LED hit the market, but if you look around now, everything has a blue LED. So just because somebody says something can't exist, and they're scientists and they're engineers and they're really smart and they've been doing this forever, doesn't mean it can't happen. And so the blue LEDs is my favorite example of that, because at this point, if you look around, everything's got a blue LED, when literally 20 years ago that was impossible. Science has proven it would never happen. So I just throw that out there. Let's see. Okay, so I'm done with this presentation part, but I did want to draw out a couple things for you. So if I go over here, got this nice little Jamboard here, and let's just pick up this little magic pen. Okay,